All right, today we're going to talk about the Bronsted-Lowry acid and base theory. This is the second theory that you have in the notes. The first theory we talked about yesterday was the Arrhenius theory, which meant you had an H plus or a hydrogen ion in solution for an acid, and you had the hydroxide or the OH negative for a base. Also, what you want to be able to know, to be able to explain, are the properties. So just as a review, make sure that you go back and review the properties of acids and bases, and you're able to list those, from memory. All right, so today with the Bronsted-Lowry theory, this is the second acid-base theory that we need to know. For some reasons, questions normally don't mention the name Bronsted-Lowry. What they'll do is they'll describe it or call it an alternate theory or an alternative theory. So I have no idea why they don't refer to it by name. They just don't. So that's just what you have to pay attention to. So we started talking about the hydrogen ion in the Arrhenius theory. Now with Bronsted-Lowry, that hydrogen ion is going to show up again. You're going to see that we use the word proton to also represent a hydrogen ion. Okay, so why can we do that? What's the reason we can do that? So what I want to show you here is a hydrogen ion versus a hydrogen atom. Actually, we'll start off with the hydrogen atom. Okay, versus a hydrogen ion. Okay, so since they're both hydrogens, they both have one proton. Okay, that's the identity of the element. So I'm going to put one proton in the nucleus for each one of these. Now the term atom, if you remember, means neutral. It means overall the whole thing has a zero charge. Ion means it has a charge. Okay, means that the substance gained or lost electrons, and now it is no longer neutral. It's got a positive or negative charge. In a hydrogen atom, since it's neutral, you also have one electron. And that electron was traveling outside of the nucleus on that energy level. The ion, though, all right, being on the left side of the periodic table, hydrogen likes to lose its electron. So the hydrogen ion now has that H plus 1 charge, and that's the notation that we use. So when you look at why, we can say that a proton is the same thing as a hydrogen ion. Well, you take a look at that. Hydrogen ion is just a proton. That's all you got. All right, so that's why we're going to use that term interchangeably during this part of the unit. Okay, so the definition for the Bronsted-Lowry theory has to do with whether or not a substance is going to donate or give away a hydrogen ion in a reaction, or if it's going to accept or gain a hydrogen ion in a reaction. So this theory is useful because there are substances that behave like acids and bases, but they don't have that typical H plus and OH negative formula or ion in their formula. So the Arrhenius theory is a little bit easier to spot when you have that H and that OH. The Bronsted-Lowry theory kind of covers all those other substances that don't have that. So let's take a look at a reaction here. In order to figure out what the Bronsted-Lowry acid or the Bronsted-Lowry base is, we have to look at our reactants versus the products. We have to see which reactant gained a hydrogen ion and which one lost one. So basically, one reactant will lose an H and the other one will accept it. That's all that's happening here, is one hydrogen ion moves from one thing to another. So we have to figure out what the conjugate pairs are. Okay, so the conjugate pair would be a reactant and a product that's different by one hydrogen. Okay, different by one hydrogen. So if I take a look, I have NH3. Well, if a product is going to be different by one hydrogen, there's going to be either one more hydrogen or one less. So I'm looking for NH4 or NH2. Well, right here I have NH4, so that's why I have that bracketed off. That is our first conjugate pair. The H2O, I have two hydrogens and an oxygen. Well, I'm looking for either H3 or just one H. And over here, I just have one H with that oxygen. So that is my other conjugate acid-base pair. So now I have to see who is gaining and who is losing the hydrogen ion. So I have NH3 turning into NH4. I have H2O turning into OH. Well, since H2O loses a hydrogen ion, it gives it away. That H2O, we would say, is donating the proton. Okay, the H2O donates a proton. The NH3 turns into NH4. So the only way NH3 can turn into NH4 is by accepting or gaining that hydrogen. So we have it written out here. NH3 turns into NH4. So therefore NH3 accepts the proton. So in this particular reaction, we would say that NH3 is the base and H2O is the acid, based on that hydrogen going from the H2O over to the NH3. So we got two more examples at the bottom here. The first one, we have HCl plus H2O produces H3O plus and Cl negative. So I'm going to find my conjugate pair first. And I know we have the answers here, but I'm going to show you how we're going to get to that. So I have to find my conjugate acid-base pair. If I start with HCl, I'm going to look for a product that either has one more H or one less H. Okay, so either H2Cl or just Cl. And that's what we got over here. So the HCl and the Cl negative, that's one conjugate pair. H2O, just like we said before, we're either looking for H3 or just H. Well, since I have H3 here, that again is different by one H, so that's our other conjugate pair. So what happens here? HCl donates or gives away its hydrogen to turn into Cl. Okay, so we are going to put a little note here. Donates the H plus. That HCl donates the H plus. H2O accepts the H plus in order to turn into H3O. So since HCl donates the H, we're saying that HCl is our acid and H2O is our base. All right, and finally we have H2SO4 plus H2O, and that is going to produce H3O plus HSO4 with a -1 charge. So let's find our conjugate acid-base pairs first. I got H2SO4. Well, that's going to be paired off with HSO4. Okay, so this is different by one hydrogen. H2O and H3O are different by one hydrogen also. Everything else is the same. So now I have labeled here that H2SO4 behaves as the acid. Well, the reason why, it goes from H2 to H. So again, that first thing there donates the H plus. The H2SO4 donates the H plus, therefore that is your acid. The H2O turns into H3O, so that means it accepts the H plus. So H2O is going to be the Bronsted-Lowry base. All right, so now I attached a page with some review questions, and you could either copy that down or print it out. And I'm going to walk you through the first couple of reactions. There's a total of 10 practice problems there. I'm going to walk you through maybe about 2 or 3, and then I'm going to have you finish up the rest and check the answer sheet for the remaining questions, just to get that practice with the Bronsted Lowry acids and bases. All right, guys?